So what we've been interested in this work is to explore the impact of a model's misspecification in a model-based test of bioequivalence. The classical test for bioequivalence is the two one-sided test on two parameters of interest, AUC and Cmax, so the area under the time concentration curve, and the maximum concentration. To perform this test, what we do is that we compute a treatment effect beta, and then we perform two VAL tests by comparing this beta to a threshold. This threshold has been fixed to log 1.25 by the regulation authorities. There's two ways to compute this treatment effect beta. The traditional approach is non-compartmental. That means we compute individual parameters, which has the advantage of making no model assumption, but it's not appropriate in case of sparse sampling. For example, if we only have one sample by patient, computing an individual Cmax is complicated. In this case, what has been proposed is to use a model-based approach, which means making a model assumption, structural pharmacokinetic model, and using nonlinear mixed effect models to compute treatment effects and their standard errors. Classically, the standard errors are estimated asymptotically from the Fisher information matrix in both NCA and MB approaches. So what we've done is that, first of all, we worked on a real case study of a monoclonal antibody, and then we performed simulation. So first, on the real case study, we have a monoclonal antibody with different level of dose and two different formulations, and we want to assess the bioequivalence of these two formulations. So what we've done is that we performed NCA toast and MB toast on this original rich design data, and we also performed MB toast on a sparse subset of the data to see if MB toast was robust to the sparse design. What we found is that NCA toast and MB toast give approximately the same results on the original data, and we can also see that MB toast is robust to the sparse design. The results are always the same. In red, the bioequivalence is not assessed. In green, it is assessed. So the results of MB toast are robust, even though the PK model selected was not the same on the rich data and on the sparse data. So we wanted to further investigate that. That's why we've performed a simulation study. These simulations were inspired by the case data. On rich design simulated data, we performed NCA toast and MB toast to compare them. And with MB toast, we used two different kinds of models, a two-compartment model close to the one simulated, and a two-compartment model with a way to model the treatment effect that was different. On sparse design simulations, we only performed MB toast, and we compared two PK models, a two-compartment model close to the one simulated, and a misspecified one-compartment model. In both cases, we investigated the relevance of adding a model selection step. So what we found on rich data is that when using a model close to the one simulated, we have results of MB toast that are close to the one obtained with NCA toast and close to the nominal value for the type 1 error. But when we use a misspecified way of modeling the treatment effects, then we see that the type 1 errors are inflated, in this case on AUC. On the sparse design simulations, what we see is that when we use a model that is close to the one simulated, the type 1 errors are still controlled. But when using a one-compartment model, this time we see inflated type 1 errors on Cmax. In both cases, rich and sparse design, what we've seen is that if we add a model selection step prior to the toast, in most cases, we select the model that is close to the simulated one, which ensured a type 1 error that is controlled, that is close to the nominal level. So the conclusion of this study is that MB toast appears to be a robust alternative to NCA toast in case of sparse design, provided that the PK model is well specified. And that's why the model selection step is a key step in a model-based approach for bioequivalence, and it's key to maintaining an appropriate type 1 error. Thank you.